All right, hello class. Welcome to lecture 17. We're in the back end of the class now. We have, over the course of this semester thus far, considered systems within the guise of linear response. We started this class by thinking about how equilibriums respond to small static perturbations and built up from there a fairly sophisticated theory of structure of disordered systems. We then changed our attention to how initially equilibrium systems respond to time-dependent perturbations, understanding notions of fluctuations and dissipations, and building up a theory for the reduced description of a few subset of dynamical degrees of freedom embedded in a larger weakly interacting bath, formulating what is kind of like the canonical, microcanonical equivalent relation, but for dynamical properties. But that was all within a weak coupling or a linear response approximation. And so really we're going to change our view for the remainder of this class and think about how we construct theories and understand systems in instances where perturbations are large or responses are very nonlinear. Now, the kind of unified formalism we've been able to build up thus far is no longer going to apply. Largely nonlinear responses don't neatly get categorized and quantified and tackled in the same kind of universal ways. And so the remainder of the class will be more of a sequence of treatments of individual types of nonlinear responses, all of which have their own ways of thinking about them and are approached in from slightly different perspectives. At the very end of the class, we'll consider nonlinear static responses. Those most often show up in the context of phase transitions, and we'll build up a theory of phase transitions, the field theory of phase transitions, known as the Landau-Ginzburg theory. Before that, we'll think about a specific kind of nonlinear dynamic associated with barrier crossings and reactivity. But before we go to either of those places, we're going to think about the dynamical responsive systems when they are driven far from equilibrium, when the perturbation takes it away from the Boltzmann distribution that we feel comfortable working with. And so over the next 3 lectures or so, we'll think about what we can say about systems driven arbitrarily far from equilibrium. So this begins a discussion on non-equilibrium fluctuations. Now, it turns out to begin this discussion, we need to introduce another tool. It's a tool which follows directly from some of the discussions we've had on our stochastic dynamical processes. Namely, we have already thought about ways of characterizing the dynamics of an open system, either from the perspective of a Langevin equation, a stochastic equation of motion, or from its associated Fokker-Planck equation. The study of non-equilibrium fluctuations are most succinctly and most compactly, in my view, discussed in neither of those specific frames, but rather in a third, which will be the focus of the initial part of this lecture, namely by thinking about stochastic dynamics from a path ensemble description. Namely, we will take our stochastic equation of motion, like, for example, the overdamped Langevin equation, and ask not for what that individual trajectory or its average looks like, not an individual realization, nor what the distribution of points along that trajectory looks like, but rather what is the probability of seeing that individual trajectory so we will think about the statistics of those paths. What was the probability to have drawn this black path? And how does that relate to the probability of seeing that individual red path? So the object that we will concern ourselves with, call it capital X of T obs. If T obs represents the length of that trajectory in time, that object is a set of positions for all times up to T obs in some discretization delta T. So because we're starting with an underlying stochastic equation of motion, there is some finite probability for every trajectory to go through the system. We will find that a discussion of non-equilibrium fluctuations is aided by trying to assign a specific probability to that trajectory and uncover some of the symmetries associated with it. So first, we will confine our discussion to Markov processes, those like the overdamped and underdamped Langevin equations whose equations of motion are local in time. A general statement of a Markov process is to say that the probability of seeing that whole trajectory, capital X, is equal to the probability of seeing its initial condition times the probability that I make a transition between X and X at some delta T in the future, times the probability that I went from X at delta T to X at 2 delta T, etc., depending only on the infinitesimal time before the time that I'm at. So namely, the whole probability of observing any trajectory in a Markovian process is just a product of transition probabilities to go between states of the system at adjacent points in time. So the fact that the dynamics are Markovian strictly means that the transition probability is independent of how the system arrived at exit I delta T. The transition only depends on that current state of the system. Such that the total transition probability is then just this product of individual transition probabilities. If the system were non-Markovian, if there was a memory, the equations of motion for the generalized Langevin equation tells us that the transition of a system from one x at one time to another x at another time not only depends on local information in time, the forces, the specific noise drawn, but also that convolution of the time-dependent friction with the velocity. So the transition probability would depend on times into the past with an extent that depends on how quickly that memory kernel decays. Now, this restriction to Markovian processes that we'll concern ourselves with is not a necessary restriction. One could formulate everything I'm going to tell you about for non-Markovian systems. It's just a little more cumbersome. But also, it should be intuitive to you that this is a pretty reasonable thing to do because, for example, Newtonian trajectories are Markovian. I could write down the probability of a transition between x of delta t and x of 0 for a Newtonian trajectory. Newtonian trajectories are deterministic. They don't have any random noise associated with them. So that transition is either 1 if I would deterministically go between x of 0 and x of delta t. Otherwise, it's exactly 0. If I don't draw exactly the right velocities and I'm at the exact right position, I will not go between x of 0 and x of delta t. So the probability of seeing that transition would be 0. However, if those are the right velocities and positions to take me between x of 0 and x of delta t, I will see that with probability 1. A way to write down this transition probability is to act on x of 0 with a propagator, the von Neumann, or excuse me, the Liouville propagator, over a timescale delta t that will then transition x naught to x of delta t. So that transition probability is singular owing to the determinism of Newtonian trajectories, but it's still a valid way to think about a transition probability in a Markovian system. Those singular transitions make working with deterministic trajectories a little complicated. So we will, in the following, consider a stochastic equation of motion, like an overdamped Langevin equation. And let's see if we can write down the probability of observing a whole path, a whole trajectory of the system evolving under that Langevin equation. Okay, so in one dimension, an overdamped Langevin equation satisfies an update rule for x that depends on a deterministic force and a random force called the deterministic force F. Call eta the random force. And that random force has to satisfy a Gaussian process with a mean 0 and a variance which imposes the temperature. So as usual, this gamma is the friction. And that random force has a scale that depends on that friction with a prefactor kBt. So naturally, in the discussion of the probability of observing a path is a scale, at least to start with. We'll introduce things discretely. So in time, let's introduce a time step, delta t, and try to work out from the Langevin equation what that update rule between positions a time step away are, these links. So a way to discretize this Langevin equation would be to take a finite difference for the time derivative. We can evaluate that f at one of the endpoints. Now, eta is something which is itself not slowly varying. We can imagine that the force varies slowly enough in time that we can choose a delta t such that it doesn't matter if we reference it to x naught or x of delta t. So let's actually do this in a different way. Let's integrate this equation over some small delta t. So just from the fundamental theorem of calculus, that will give me a boundary term. If I assume that f is slowly varying over delta t, I could bring it out of the integral. But how do I treat this integral over eta? Eta is something which is rapidly varying. It's singular, it's delta function at one time and not the other. Well, if eta is a Gaussian process, an integral over eta is a sum of Gaussian random variables. The sum of Gaussian random variables is also a Gaussian random variable. Turns out you can work out the statistics of the sum of eta, and integrating it over a small delta t just changes its statistics by a factor of delta t. So that's something you'll work out in the homework. So fear not if it doesn't make sense. Suffice to say that I can take a Gaussian random variable and multiply by it the square root of a number, and that essentially is changing its variance. And that's all we do when we integrate over a random number. If they're independent, the sum of a Gaussian random number has a mean that's the same and a variance which is scaled by the number of terms in that sum. Okay, so now we have a discrete update. We go from x of delta t to x, from x naught to x of delta t. Depends on the force, which is uniquely determined by x naught, and this noise. So what is the probability of making this transition? What is the probability that I actually do get to x of delta t, given I started at x naught? So that conditional probability can be written out as an average over a delta function that says, that returns 1 if x naught goes to delta t and returns 0 otherwise. A way to enforce that is to say that this equation is true, that x of delta t is equal to x naught minus f naught delta t over gamma minus delta t over gamma eta naught. Averaging that over the noise, so the only thing that's fluctuating in the above equation is eta. Eta is a random variable. I have to ask, essentially, what is the probability that I drew the correct random noise such that that equation was true? But eta is just a Gaussian random variable, so this is just a Gaussian integral, and we know how to do those. So the probability of making that transition is the probability I drew the correct eta, the probability I drew the eta that I need. It's just an integral over that probability distribution with a delta function that enforces the correct eta, the correct random variable. As p is Gaussian, that delta function will just kill the integral and replace the argument of that probability with the solution of etas equal to those variables. Namely, I will get that the probability of making that transition is itself Gaussian. That depends on the force at that position, the displacement I make, delta x, and has a variance that is twice kBt gamma and depends on the time step. So we can rearrange this a little bit to ask for the probability of making a displacement, delta x, which is an exponential minus, I can pull the beta from the denominator of the argument of that exponential, a gamma and a 4 delta t. I have delta x minus f of x naught delta t by gamma squared divided by that normalization constant, which also depends on delta t. So that tells us that the probability, if I make many realizations of this process, drawing different realizations of my random variable, the probability of making a specific delta x is itself a Gaussian distribution. Owing from the linear relationship between x and eta. It's got a mean that just depends on the force, and a variance that depends on the time scale over which I look for that displacement, beta and gamma. So the picture, imagine I start at the origin. I want to get a trajectory that ends up at a specific value of delta x. The probability that that happens depends on the drift over which x is pushed by, which is encoded by the force. And in addition, the spread coming from the distribution of random variables, random noises that are added to the system. All right, so how should we think about the probability of making this small change in position? To get some insight, let's consider the probability of making a jump in the a forward jump relative to a backwards jump. So P of delta x divided by P of minus delta x. Well, the normalizations will cancel. I'll be left with e to the minus beta gamma over 4 delta t. Delta x less f of x naught delta t by gamma quantity squared. It's probability of going forward, drawing the right noise that takes me between x naught and x of delta t. Probability of going backwards minus delta x if I factor all that out, only the cross term between delta x and f will remain in the numerator, not be canceled from the numerator and denominator. I will get e to the beta delta x times f of x naught. F, you remember, is minus the gradient of a potential if this is a conservative force, which to a good approximation is minus delta u over delta x if delta x is small. So what we've just found is that the ratio of going forward a small step to the ratio of going backwards a small step is e to the minus beta delta u. Namely, the probability of making a transition or its reverse is given by a ratio of Boltzmann factors. Now, this is, on one hand, not super surprising if we think about what we're actually doing for a second. The equation of motion, this overdamped Langevin equation, came about to us from considering some tag degree of freedom that was in contact with a heat bath, a bath that was linearly responding and did not depart from equilibrium. For energy to be exchanged with that bath between it and the system must encode the equilibrium thermodynamics of those energy flows, given the bath is always at equilibrium. So if, in order to make an excitation in the system to cause this X degree of freedom to go up a potential, or to release some energy to let it go back down the potential, must mean that that energy leaves the system and goes into the bath. And from the bath's perspective, the probability that that energy comes in or out must exactly be Boltzmann distributed. The bath has no memory, so it equilibrates infinitely quickly, and it is at equilibrium at a fixed temperature. So it is that Boltzmann factor with the temperature of the bath that dictates the relative likelihood that the energy comes in or leaves. So this is a microscopic statement of detailed balance. More generally, detailed balance is a statement that the dynamics preserves or are constrained such that they ensure equilibration. A detailed balance dynamics are a sufficient condition to preserve an equilibrium state. Namely, if I imagine the probability to go between two arbitrary sets of arbitrary states denoted n and n prime, the ratio of going between n and n prime relative to making that transition in reverse, if detailed balance holds, that this is the ratio of the probability of being at n prime relative to the probability of being at n. That's another way of stating stationarity. If I move those to the right and left-hand side, the probability of going from n to n prime times the probability that I was in to begin with is balanced by the probability of leaving n prime to go to n times the probability that I was in n prime to begin with. That says that between states n and n prime, there is no net flow of probability. The probability currents that take me between n and n prime are exactly balanced in the equilibrium state set by those dynamics by the probability current occurring in reverse. A strong statement of equilibration is that this holds for all n and n prime. If I sum, for example, over all n, PEQ of n prime is independent of that sum, it comes outside. The sum over all exit probabilities, all exit states that n prime can go into, if that is a normalized distribution that results in just 1, and thus if I sum over all exits out of n prime to n, or all exits from n to an arbitrary n prime, I will evolve to an equilibrium distribution. So detail balance is a stronger statement than this statement above of stationarity. If it holds for all pairs n and n prime, that this implies that there are no cycles within an equilibrium state. There's no net probability flow within any pairs of probabilities. And this is a strong statement concerning equilibrium. So going back to our overdamped Langevin equation, plug in here, sorry about that. We can note that while we've done this for discrete steps, that Markovian approximation, or that Markovian assumption up here, if we know the probability of making an update between pairs adjacent in time of states, the total probability of the trajectory is just the product of those individual transition probabilities. We've worked out what those individual transition probabilities are. They're just Gaussian, the probability of drawing the right noise. If I take a product of exponentials, that's an exponential of a sum. In a continuous limit, that sum could be transformed into an integral. So the probability of observing any trajectory should be proportional to the probability of drawing the right set of noises that I see that trajectory. The probability of drawing a specific set of noises is just the probability that I draw from the Gaussian distribution that specific set. In general, the probability of seeing a specific trajectory in eta in those sets of random noises is a Gaussian. If it were non-Markovian, that Gaussian distribution would have some correlation function, call it chi of t and t prime, which in this Markovian limit, only t equals t prime are correlated, and thus the probability of drawing a set of eta from 0 to t is just the probability e to the minus 1/2, that integral eta squared divided by its variance, kbt gamma. So in the continuum limit, we see that hiding under the rug of this Langevin equation is a Gaussian field theory, though one in which that exists in time with a very specific correlation function, the correlation function of the bath, which was assumed to be delta correlated, in which case the probability of drawing a specific set of eta is just the probability of drawing a specific set of etas at those individual time points. Noting that to see an individual trajectory, eta must satisfy this equation for some arbitrary force f of t. Let's call it f of x of t comma t. Might not just be a gradient force. Substituting that equality for eta, we see that the probability of observing a whole trajectory of the system in this continuum limit is proportional to e to the integral from 0 to t, and substituting eta in for its equation of motion, eliminating eta, we have the likelihood now of tracing out a specific trajectory. And indeed, it is a Gaussian with an integral in time. So this is now a path integral description of our stochastic equations of motion. The argument of this exponential is often referred to as the stochastic action associated with that process. In the limit that t goes to 0, or gamma goes to 0, we will end up with a probability that is very peaked for x dot is equal exactly to f. So the probability would be determined by just its minimum action path, the path that satisfies that equality. X dot is equal to 1 over gamma f. So in the limit that the noise is low, because t is small, we will recover a deterministic evolution. But in general, for a finite temperature and a finite gamma, there is a distribution of paths that is Gaussian distributed. Okay, so with that under our belts, we now have a path integral description that we can use to uncover a few deep statements about dynamical systems, complex dynamical systems. And the first of these will be to derive the so-called Crooks fluctuation theorem. So let's ask a simple question like that we've already done. Let's imagine I want to ask for the probability of observing a trajectory given some initial condition relative to observing that trajectory in the reverse direction of time. So what I mean by this is I can start at x naught. I could propagate a trajectory, end at some xf that is propagating in the forward direction of time. The probability of seeing that whole trajectory is the probability that I drew those random noises that were commensurate with the forces acting on X, such that I saw that specific evolution, I could then ask, what is the probability that if I started at X naught, or at XF, the endpoint of that trajectory, and integrated, what is the likelihood that I would have traversed that exact same path? So from our stochastic path integral, we know how to write those down. Normalizations cancel, which is nice because they get a little bit awkward in the continuum limit. So working out that whole Gaussian, I'll have a gamma x dot squared. You can factor out the beta. And this will be over 4. I have a plus f of x potentially being time dependent, x dot divided by 2. Sorry, that's a minus. And over gamma. And then an f of x, possibly t, squared over 4. Gamma. That's the probability that that path was drawn in the forward direction. Reversing it, well, the only thing that's odd under time is x dot. That's an odd variable, but if I square it, that first term remains the same. X dot here changes its sign. I have plus f of x and t x dot over 2 gamma. And f, if those forces are the same in the forward and reverse trajectories, it remains the same. So again, this term cancels that term. This term cancels this term. The only thing I'm left with are these terms. Flipping the sign by bringing it up in the numerator, I get an exponential of minus beta. Now they add, the 1/2s cancel. Sorry, those gammas should have gone away. And now I have an integral from 0 to t prime, x dot, f of x and t. So we're left with an integral, e to the minus beta, the integral x dot f. So let's consider the case where this f of x and t is just a gradient force. It's the derivative of a potential with respect to x. That would mean that the probability of observing the trajectory in the forward direction, conditioned on starting in x naught, relative to the reverse direction, which I've denoted as x tilde, should have labeled that here. So here's the reverse trajectory, here's the forward trajectory. That is equal to, if f is a gradient, x dot is dx dt. The force is du dx with a minus sign. That is the same thing as du dt integrated over t is just e to the minus beta delta u, where delta u is x, u of x f minus u of x naught. I messed up a sign somewhere. Ah, this was a minus, which makes this a plus and that a minus. So we find detailed balance again, namely that the probability of being at xf, taking xf all the way and retracing our steps to x naught, is balanced by the probability of starting at x naught, given a Boltzmann distribution, and tracing that path up to xf. The change in the potential, again, is coming from energy that's flowing between the system and the bath, and so the bath is mediating a thermal transition that in principle could change the potential. So this is, again, just another statement of detailed balance that comes about simply, in this case, that the force is a gradient force. But let's ask about this force being something more general. So what if f of x and t is not just a gradient force? Maybe it's some time-dependent external force that I'm manipulating the system with. So let's write f of x and t as a piece which is gradient, the derivative of some potential, plus some piece that is explicitly time-dependent. Some time-dependent protocol that I'm acting on the system. So now the change in the total in the energy of the system has two components, du dt, because u is being acted on by both an external force and there's some gradient force. The change in the energy of the system, let's use u, is both due to how u changes with x and how x changes in time. Maybe clarify that this u is a u that depends both on x and this lambda. X changes with time, and so that affects a change in u, the potential. And this is an overdamped system, so there's no kinetic energy, so this is just the energy of the system. But because lambda changes in time, there's some change in u due to lambda multiplied by how lambda changes in time. how U changes with this external protocol that we are imagining to manipulate is distinct from how U changes due to just how the thermal motions change the position of X and how that then affects the change in the energy of the system. One is something we are controlling, one is something we are not. It's natural, therefore, to say that the total change in the energy, U dot, is decomposable into a piece that we are controlling, call it W dot, and a piece that we are not. Changes in the energy of the system modulated from energy flow between the system and the bath, call it Q dot. We would associate the former with heat and the latter with work. So making that identification that the total change in the energy is the change due to heat, energy exchange with the bath, mediated from this thermal bath, which is kept at a finite temperature, at a fixed temperature. But in addition, if we were to apply some time-dependent protocol, we would be doing work on the system, and we can affect changes in the energy in that way also. So more generally, the ratio of the forward trajectory given some initial condition relative to the backwards trajectory is equal to, if that force has this gradient piece and a non-gradient piece, X dot, the gradient in the force, or the X dot times the force. This is thus its integral gives me just the heat release. This is what's known as the Crooks fluctuation theorem. It says that even a system driven, I'm applying some time-dependent protocol to, the fact that it is exchanging energy with a bath that's at a fixed temperature means that even if I drive the system with some wild external protocol, the underlying microscopic reversibility of that system manifests in a constraint that tells me that the likelihood of making some trajectory relative to reversing it is just given by the heat flow mediated between the system and the bath. Now, this statement, the Crooks fluctuation theorem, in some perspective, is a microscopic statement of the second law. To see that, consider the so-called integrated fluctuation theorem. If I take an integral over all trajectories, the probability of observing that trajectory. Weighted by bring the exponential of minus the heat over to the right-hand side. It's dependent on that path. Through the Crooks fluctuation theorem, this and this is equal to the reverse. The right-hand side of this equation is 1 by normalization. The left-hand side is thus the average. And so I have an integral relationship that says that e to the beta q averaged over all trajectories satisfies an equality, which is just that exponential average is just unity. From Jensen's inequality, the exponential is a convex function. So e to the x averaged is always greater than or equal to e to the average of x, which means that e to the beta average of q is less than or equal to 1, or that q minus is greater than or equal, taking the log of both sides, to 0. The heat flow into the bath has a definite sign. Given that the bath stays at equilibrium, the heat flow into the bath is the change in the entropy of the bath, which tells us that delta S, the change in the entropy, is strictly positive, which is just the second law of thermodynamics. And this is what we mean by the Crooks fluctuation theorem being a microscopic statement of the second law. It tells us that not only on average is entropy increased, but in a detailed way, the fact that entropy increases on average encodes a symmetry in microscopic trajectories that constrains the likelihood of seeing a time asymmetry, a distinction between a forward trajectory and its time reverse, a distinction between the forward and backwards direction of time. If I could tell the difference between a trajectory in the forward direction or one in reverse, it must therefore be that there is a significant amount of heat released. If there's no heat released, the forward and backward trajectories are equally likely. I can't tell the difference between them. If we think back to an ink drop experiment where I drop a little bit of ink in the top of a beaker, I could tell the direction of that trajectory by playing that movie forwards or backwards. It seems odd if the ink gets sucked back up into the droplet. Associated with that change is a change in entropy. I get more entropy associated with distributing those dye molecules throughout the beaker. Entropy increases, the heat increases. this says that even microscopically on an individual trajectory level, the likelihood that I start in a concentrated droplet and traverse dynamically filling that beaker is exponentially more likely than to have seen that trajectory occur in the opposite direction. With the Crooks fluctuation theorem, we can also prove another important identity. Consider a time-dependent force that follows a specific protocol. One in which it is held fixed at some lambda naught for times less than some origin. It is ramped with some protocol lambda of t for times greater than 0, but less than some observation time, at which case it is set to another constant, some lambda f, for t greater than some observation time. This means that we start, if we only do something time dependent, we start in an equilibrium under a potential that depends on lambda naught. We end at long times, long compared to t obs, in an equilibrium, now one specified by lambda f. And in the middle, we could leave an equilibrium distribution of states owing to the fact that lambda changes in time and in a way that we're not going to assume is small or perturbative. So taking our previous results, we found that 1 was equal to an integral over reverse trajectories, the probability of seeing that reverse trajectory given I started at some xf. I can now look at the total trajectory probability by multiplying that by the probability of starting at some xf and integrating that over all endpoints xf. That is still normalized. That says that the probability of seeing a full reverse trajectory is 1. I can multiply top and bottom by the probability of reversing that trajectory, now going in the forward direction of time, with some initial condition x naught. The ratio of the transition probability of seeing a specific trajectory from the Crooks fluctuation theorem, that's e to the beta q. If I start and end at equilibrium, that is Boltzmann distributed that Boltzmann distribution. What's the probability of seeing xf, which is e to the minus beta u divided by some partition function. I could put that partition function upstairs by adding to it the free energy at lambda, what do I call it, f. If I also end at equilibrium, the same is true there, just with the minus sign. And now I have an integral over all trajectories in the forward direction. All of that is now equal to 1. Now, assuming that my space is well defined, there are the same number of trajectories forward and backwards, the same number of configurations forward and backward. So I can do a change of variables. There's no Jacobian associated with changing them. This is some delta f. I have, in addition, a q minus a delta u. Q minus delta u, well, that's what we mean by work. With minus. I have a plus beta delta u and an integral over the probability of seeing those trajectories. That is then just an expectation value of e to the minus beta w plus beta delta f. Rearranging that, e to the minus beta w is equal to e to the minus beta delta f. And that is very surprising. That says that I do some work over the course of this external time-dependent protocol that takes the system in general away from equilibrium. I'm not doing this quasi-statically. I'm not doing this reversibly. I am taking an arbitrary path between two equilibrium states. Those two equilibrium states have different free energies, delta f. But if I measure the work that I do over the course of that transition in the right way, namely with an exponential of minus beta that work, I will recover the equilibrium free energy difference. This is what's known as the Jarzynski equality. It implies the Clausius statement of the second law, again, from Jensen's inequality. This says that e to the minus beta delta u is greater than or equal to e to the minus beta work on average, or that the work on average is greater than or equal to the free energy difference. That's another statement of the second law, that I always have to do more work than is required to see a transition in a finite amount of time. So again, encoded now in the statistics of trajectories is an equality that holds arbitrarily far from equilibrium for arbitrarily large perturbations, for arbitrarily swift perturbations. There's no constraints here on what lambda of t is. Now there's a trade-off, of course. The fact that this is an exact result comes at a cost. If W is large, if the work is large, if I'm doing this macroscopically, there is little chance that I will be able to actually see the rare fluctuations in the work that would make this equality valid. If W is large and positive on average, then I will not saturate that equality very often. However, if the system is small and the amount of work I do is small, that's an exponential average one can potentially actually evaluate. Implied by the route that we got here is another relationship, that the probability of seeing some amount of work relative to its reverse is equal to minus beta, the work plus the free energy difference. Or where those two are equal, where it's equally likely to see the forward amount of work or the backwards amount of work, that work value is equal to the free energy difference. This is another fluctuation theorem, and one that has actually been observed experimentally, validated experimentally. So let's take the last little few minutes of class to actually explore this. First, one typically, when you grow up and think about thermodynamics, don't think about work as a fluctuating quantity. So to understand what we really mean by work being a fluctuating quantity, we have to think about what we're averaging over. Here, the protocol is determined. I do the same lambda of t every time. However, different realizations of the bath, different fluctuations from the bath, result in different random forces acting on the system that will push it around. And through correlations with those interactions and the external protocol, result in different amounts of work being done. This equality states that implies that while on average, the average work that I do on the system is greater than the free energy difference, for the equality to hold, it must be that there are instances where the amount of work done on the system is less than the free energy. That's the only way to average that exponential and get something which is an equality. So let's actually explore that. So here's a kind of canonical example of a microscopic realization of being able to study the work statistics of a system. This is a kind of character of a pulling experiment whereby I, with optical tweezers, manipulate some polymer like a protein by pulling it apart. I could pull it apart at some finite speed. And by measuring the restoring force that that polymer acts on the bead with, I can measure the work that I'm doing on that polymer. So this is a simulation where I know what the reversible work is from the model that I've coded up. And I can compare that reversible amount of work to the instantaneous realizations over these trajectories of the amount of work that I actually do. So let's play that. I pull the polymer apart with these little green beads. The green line is the amount of work that is done. The blue line is the reversible work. And typically, the amount of work being done is much larger than the reversible work. I'm pulling it at a finite speed. However, it should be possible, given the Jarzynski equality, that that work is less than that. Hey, look at that. Didn't take too many times in this small system to actually see a realization where the amount of work done was less than the reversible limit. That seems like it's a violation of the second law, which says that the work is greater than or equal to the free energy difference. But thermodynamically, what is implied there is an average that only typically is the work done on the system greater than the free energy difference. There could be realizations, as we just saw, where the work done on the system is less than the free energy difference. Indeed, if I was to do enough calculations, averaging the exponential rapidly varying function, kind of complicated to do, but in principle, one can do that. And irrespective of how fast you're pulling it, you would be able to converge the free energy difference from very far from equilibrium realizations of this external protocol. This is, in fact, not science fiction. Not long after the Crooks fluctuation theorem was discovered, scientists here at Berkeley, including a team led by Carlos Bustamante, actually realized it. So shown here is a microscopic polymer pulling experiment. This is in this case, a little RNA hairpin, where they can measure the extension, they can measure the restoring force, and thus the integral under the curve is the work. They could do this experiment enough times to generate statistics of the work. Different realizations gave you different amounts of work. They could do it in the forward direction, the unfolding direction. They could also take the system unfolded and force it together to fold and measure the work in that reverse direction. From that fluctuation theorem, the symmetry of the work in the forward direction and the reverse has a point at which they will be equal, where those curves will cross, shown here as the dotted line. Right here. Where those curves cross, therefore, is the equilibrium folding free energy difference, the free energy to fold this little RNA hairpin. These and other realizations have demonstrated that this Jarzynski equality and the Crooks fluctuation theorem are right, that in many instances you can drive the system far from equilibrium, and a thermal bath imposes a constraint that relates those two directions in time. All right, that's all I have to say for today. We'll continue in this basic direction over the next few lectures, thinking about systems driven far from equilibrium, the symmetries implied by microscopic reversibility, and how this gives us some insight into very nonlinear behaviors of systems. Okay, but with that, that's all I've got. I'll look forward to seeing you all in the small groups, and I'll speak to you then.